Welcome back, dear friends, to the second part of the series on how to make an Arduino controlled clock with moving arms controlled by stepper motors. So David has made a beautiful wooden enclosure for his clock, but he's just struggling a bit with the programming and connecting stepper motors and all that. That's the idea of this series of videos. Right, today we're going to talk about how to connect things to Arduino outputs so it can get things moving. I'll start off by going through three common types of motor. I thought it would be useful, it's a good opportunity to do that. I will try not to waffle on. I will put everything into chapters with links in the description so that you can skip all the boring bits and get hopefully to an interesting bit. So the three types of motor I'm going to look at is a DC motor, a servo motor and a stepper motor. Let's start with the DC motor. So a DC motor is one that you can connect to, in our case, a low voltage, say 5-10 volts DC. If you connect it up one way, the motor goes one way round and round and round forever. And if you connect it up the other way, it goes backwards, so to speak. And they are very fast if they're not geared. Let me show you. These are lovely little DC motors. They run off 3 volts, and I use them in the motorised Kraken gauge because they're perfect for that, because they're very quiet and they can run. They use very little electricity. They can run off like sort of 2 AA cells for weeks. So you can see they are absolutely great for spinning things very fast, not necessarily needing that much power. Now, to slow them down, you can use gears, because you can buy a version, lots of different types of versions that have built-in gears, which are lovely. That means the output goes much more slowly and has much more torque on it. Problem is, always a problem, the noise. This is a 12 to 24 volt motor, so I'm running it off 12 volts. And if you mount it, if you hold it in the air, it's not too bad, but if you fix it down, it really is noisy, and you just can't get away with that with these gears. This one, you can see how fast the actual motor's going, and by the time this has got 100 to 1 gear ratio, or the other way around, so these are going 100 times slower. And you can see that if I try and stop it, there is absolute no way. So when I was originally designing the motorised Kraken gauge, I did think about using gears, laser cut gears, but it was so noisy, it was ridiculous. So in the end I came up with a cunning plan of using a drive belt, like a rubber drive belt, and just using this as the first pulley, so I could get as much slowing down as possible, if you like. They're also perfect to use on the epizooscope, just to drive all the belts and the gears and the levers and things down, because again I used a really small pulley on the first one and then driving a much larger pulley. So how do we control these? I mentioned last time that the Arduino has a number of different GPIOs, which stands for general purpose in-outs, which means that you can tell most of them from within a sketch, which is what you call a program in the Arduino world, to either be an input or an output. You can have a digital input where it will sense 0 and 5 volts, because it works off 5 volts. You can have a digital output where it can switch between 0 and 5 volts. If you've got a little squiggly bit on them, like those ones, that's a pulse width modulated output, where you can feed it a number between 0 and 254, and it will vary the outputs to basically be on and off more or less time per pulse. I'll come on to that a bit more later. That's brilliant for controlling the brightness of LEDs or the speed of motors and things. That's nice. Or you can even have an analog input, and there are several pins just for that. They can also act as outputs and other things, but analog inputs where they can read a voltage between 0 and 5 volts, such as from a potentiometer or something like that. Right, so it would seem like the best idea would just be to connect one of these to 0 volts and one of the outputs set to digital output. Thing is, all would not be well, because these Arduino outputs have a maximum, can output a maximum of 20 milliamps. So that's 20 thousandths of an amp. It doesn't sound much, but you can do an awful lot with that. It's enough to light an LED or control numerous data bits and bobs. Not enough for this, because this will draw about 50 milliamps at least, and if it's under load it could go up to sort of 100 milliamps. If you tried doing that, it would immediately vaporize the components inside the Arduino. You probably wouldn't release the magic blue smoke, but you would certainly destroy one of the input outputs, possibly worse. So what we need is a way of getting that to switch enough electricity to control that, or indeed a bigger one like that. The simplest way of achieving that would be to use a transistor. There are lots of different types, so I won't go into that, it's not really in the scope of this video. So we have ground at the bottom, which is 0 volts, I'll refer to it as ground usually if I forget, and plus 5 volts at the top. There's the Arduino connected between them. You have the output running through a resistor to limit the amount of current flow, so we don't go anywhere near the 20 milliamps output maximum. It's still 5 volts, but 20 milliamps. And that limits the current, and you get a little bit of current when you switch the output on, flowing through here, through the base, out through the emitter down to 0 volts. And then in turn the transistor switches on, or allows a load of electricity to flow through, much more current. Could be you know, an amp and a half or whatever with basic transistors. And then you can connect your motor here, so the electricity flows through the motor, through there down to ground. One thing to remember, I might be going about completely talking too much, but I think it's worth mentioning. If you use a motor, motors are made of a series of coils of wire inside, which electronically are called inductors. When you switch an inductor off, it creates a very large spike of electricity called back EMF. If you don't take account of that, that will shoot back through your circuit and probably damage and destroy most of it, because it can be sort of thousands of volts. So to stop that, it's really important to have a diode wired the wrong way across here. If you think about it, electricity, if it was the other way around, electricity would go through the diode rather than the motor. When you turn the motor off though, or the transistor does, all the back EMF goes through there to nothing, it just gets short-circuited. Right, so a typical transistor, I use these on a few of the kits and things, looks like that. And the higher the power that they handle, they'll have bigger and bigger heat sinks. You can get very small ones obviously as well. I know I'm jumping around a bit, so I apologise, but I just wanted to tell you what the inside of a motor looks like. Now we're talking about inductors and things. I took one of these to pieces for your delectation because I'd broken the wires off it. Inside you have the central part that looks like that. That's quite commonly got 3 coils of wire, all connected to some contacts that can spin round, called a commutator, and they sit within a magnetic field created by 2 fixed permanent magnets. Now in order to pull them round, the back of the commutator has got 2 little strips of metal, 2 conductors that push against the commutator contacts. And what it means is, as the motor turns, they switch on and off the next coil in order to pull it round. Very clever, because also the way it's wired up, they reverse the other coils, so they're constantly pulling and pushing each other round. So that's why they go as fast as they possibly can, because there's nothing to slow them down. So that's nice. Right, so as you can you've realised, I'm sure, that you can use that as a digital output, just on or off, and the motor will then run full speed or full off basically. Or you could use the pulse width modulated output. So pulse width modulation works by having a pulse of set length. That's just to represent them with little dots. The basic one on the Arduino I think is 480 Hertz, although you can adjust that within a sketch. So for each of these pulses you can decide whether it's on all the time, that would be 100%, or whether it's off all the time, which would be 0%, or you could have it sort of 10%, you could have it 90%. And by doing that, it means that the motor receives 5 volts, because this represents 5 volts. It's just how often it gets 5 volts, which is very useful for changing how fast it's going. And because it's always receiving 5 volts, the motor's sort of always working flat out, even if it's going slower. Now, it's also useful because this is a 3-volt motor. That's 5 volts. It also means you can control a 3-volt motor by working out the difference. What's 5 divided by 3? It's probably about 3/4, and never exceeding that amount with the pulse width modulation. Actually, I'll get it wired up so you can actually see what goes on. The actual values, I'm using pulse width output number 3 on the Arduino through a 1K resistor into the TIP121. Between you and the gate post, the TIP121 actually has 2 transistors in it wired as a Darlington pair, which makes it much more efficient at switching lots of electricity. Got the motor, anti-flyback diode, and then on this side I've added a potentiometer connected to +5 volts output on the Arduino and ground on the Arduino, and then the wiper in the middle goes to I/O, the analog input. Now I'm going to write a little sketch. Circuits always look so nice when they're drawn like that, and then you make them, you end up with all coloured spaghetti everywhere. But there's the transistor, the resistor, anti-flyback diode on the back, the motor connected as shown on the diagram. There's the potentiometer connected to the +5 volts and ground on the Arduino, which is fine because it's really virtually no current, and the output of the potentiometer goes to I/O. The reason for having the potentiometer is just that I can twist it and show you the effect it has on the speed of the motor. So here's the cheeky little sketch. There's setup, which runs once, and I'm just saying in the setup, pin mode I/O is analog read, pin mode 3 is analog write, which is the pulse width modulated output. I know you don't have to always use these, but I do, just because I look at setup and I can see what I'm using all the pins for. But this is the loop that's going to keep going round and round and round. So I've created a variable called potval, which is an integer, made that equal to analog read A0. And I've created another variable, an integer called pulse width modulated out. I'm going to use the map function, which is very handy. I'm going to read the value of the analog input, and I'm going to say it's going to be between 0 and 1023, and I want to map that to a value of between 0 and 255, which is what you do for pulse width modulated outputs. So I'm going to analog write to pin 3 the pulse width modulated out value. Let's see what that does. So as I turn up the potentiometer, it's not a very good potentiometer, but you can see you can vary within reason the speed of the motor. And if I connected the transistor via the resistor to a digital output, then it would just switch the motor on or off. If you'd rather not use a transistor because you want to use a ready-made module, there are a plethora of different modules capable of controlling running DC motors. Quite often they're called H-bridge controllers. And inside they basically look like these. They have 4 transistors with a motor connected between them. That means if you switch that transistor on and that transistor on, the electricity will flow that way through the motor and it will turn one way. However, if you turn that one on and that one, it'll flow the other. If you turn that one on and that one on, it'll probably blow the power supply, which is why handily they come with some logic gates. You can't do that. But that's very, very useful, and they come in all sorts of different sizes. From larger ones that handle more current with heat sinks that literally just take the outputs from an Arduino and can run quite a large motor. I think they can run up to about 5 amps, some of them, right through to very clever small ones. Here's a very clever small one. This will run a motor, but it'll also be able to be controlled by I2C. So a huge range of different types of interface available. If you need to use one of the other more complicated interfaces, then you can download a library that will help you to use that. You can get these relay interface boards where the outputs from the Arduino actually have opto isolators, so it's completely disconnected from the rest of the circuit. These little opto isolators, they have an infrared LED in one half of the case, the package, and a phototransistor in the other, so they have a physical gap between them, so they're electrically isolated. And then they have their own transistors and things to work the relays, and then the relays can be connected to high voltages and things like that, whatever, something completely different. And these boards are readily available. This one has 3/4 of its relays, because I took that one out to use in a project. A handy source of them. So to summarise, because I forgot what I was talking about, we can't use a DC motor to drive clock hands. It just would not be accurate enough. So now let's move on to servo motors. Servo motors are wonderful things. They have so many uses. They have a built-in interface and can be set to move to a certain position. So they don't go round and round and round. They usually have a movement range of about 180 degrees, sometimes a bit more, 270 degrees. But within that range of movements, you can set them pretty precisely where to go. The thing is, with my setup, I've still got the Arduino powered by the laptop USB. And I've got the servo motor powered by my lovely power supply. How does that work? Because obviously you don't really want to connect 5 volts from that to 5 volts from the laptop. Well, as long as the electricity has got a way of getting back to where it started from, it's okay. So look, here we are. USB plus 5 volts is driving the Arduino. That's connected to USB 0 volts. And 5 volt power supply is running the servo motor connected to the power supply 0 volts, which I forgot to write. And the signal is going across the middle. And the fact is, as long as you connect the grounds or 0 volts for everything together, the electricity from the Arduino can go through that wire and get back to home. So that's how you do it, and then you don't have to connect these two together. So there's my voltage supply, power supply. That's coming to run the servo motor, 5 volts. Ground coming to run the servo motor. Signal wire from the servo motor coming back to the Arduino, and the ground also going to the Arduino. And that's fine. As always, the wonderful Arduino comes with a sketch called Servo. If you go to File and you go to Examples, it comes with one that's built in somewhere. Here we are, Servo. For loop makes it go around in one direction, and then the next goes back in the other direction. Let's see, so that's 15 milliseconds now. We've slowed it down between each pulse, and it breaks up the movement, 100-degree movement, into 180 separate little steps. So you can see you can get it, and you could increase that delay, those delays, and it would move even more slowly. Problem is, they're not that accurate. If you're going to have one controlling a dial on a clock, a pointer on a clock, you really do need it to be very accurate. And servo motors vary a little bit each time, which doesn't matter in their normal modus operandi. But for something like controlling a pointer accurately, not really good enough. I used one in a clock prototype I made to move a pointer. You can see it just sitting there. Now with 3 positions it's fine, but I found, as I say, it just wasn't really 100% reliable. It varied by a few degrees each time. Funnily enough, this clock, the chronological numerator, was the forerunner of the chronological engine, because I finished this and I thought it doesn't do enough. It's not got copper pipes and fiddly bits down there. So in the end, I did overcomplicate it and added nice tubes and things of an interesting nature, and another knob, that's right, a control, because it does do quite a lot of stuff, and it just got too complicated to have a pull string. The great thing about servo motors though is you can get big ones, and you can get bigger ones than that are all metal and really, really tough, right through to the sweetest little ones. Look at that difference. Isn't that gorgeous? It's amazing. Right, I think that's probably enough before I remember some other point I haven't made about servo motors. So finally, let's broach the subject of stepper motors. Stepper motors come in all sorts of different sizes. They do go round and round and round and round in either direction very, very accurately. And you can get large ones like this, larger ones, right down to beautiful little ones like this, which I'm going to be using for this project and which I use throughout most of my projects, the 28BYJ48, because it runs off 5 volts. That's great. The way they work is unlike DC motors, where you have the electromagnets mounted on the bit that spins round within a magnetic field, a permanent magnetic field. Stepper motors work the other way around. In the middle they have the permanent magnets on the spindle surrounded by a number of individual electromagnets, windings, coils, whatever you want to call them. That means, because they don't have a commutator switch that's switching on all the coils in the right order, you have to control the coils yourself. Now that's very handy, because that means they can go as slow as you want. It also means that they have certain positions. You know that they'll have so many steps for one full rotation, so they can be controlled very, very precisely. So this larger stepper motor has 200 steps per rotation. These ones are amazing. They have, I've written in a box because I can't remember all these numbers. It has 32 steps per revolution, and then it has a beautiful gearbox on the top, which is quite unusual for stepper motors, with a ratio of 64:1, which means you can get 4,096 steps per rotation. That's amazing. And also with that much gearing, even at 5 volts, you really can't stop it with your fingers. It's got a lot of torque. One thing to point out, which I think I forgot to mention before, you can make them go as slowly as you want, because you could have 1 step per year if you wanted to, but they can't go that fast. Otherwise, if you try and run them too fast, as I found with the ukulele machine, they just judder and stutter and miss steps. I think the fastest that the BFY, whatever it's called, goes is about 12 RPM. So it's not bad. I mean, it's fine for everything that we need. This is a very good juncture to point out a very important fact. It's all well and good knowing and be able to position something, move something 4,000 whatever it is steps per revolution, but the Arduino doesn't know where it's starting from. With a servo motor, it doesn't know, but as soon as you've sent it a signal, it knows where it's meant to be, but not with stepper motors. So the first thing you have to do when you use a stepper motor is somehow let the Arduino know where it is. I can demonstrate that. If you have a 3D printer, you'll have some stepper motors. There's one filthy one there. That one drives the printing nozzle left and right. There's one at the back that drives the whole bed backwards and forwards, and there's one just down round at the side that drives a thread that lifts it up and down. And finally, you have 4 if you've got a filament 3D printer. There's one here that forces the filament through to the nozzle and retracts it as it needs to stop and start printing. Now, there's a micro switch there. There's also a micro switch hidden at the back. So when you're ready to print, you'll hear it and see them all move to their origins, the starting point. So before it did any printing, it set all of the positions, all the motors back to an origin, so that the controller inside knows exactly where it is and where to start. The laser cutter also uses 2 micro switches, but they stop working. So when I switch it on, I have to be ready with the stop button before they jam into the end and at the back. One day it's on my to-do list. I use these small stepper motors in all of my projects because they are so versatile, powerful and accurate. To let it know where it is on this machine, I come up with a cunning plan. Each time the pointer needs to move to 12, there's a micro switch, and I've calibrated, well, glued on the pointer, so that as it hits the micro switch, that is 12. So it can calculate all the other positions, but then every time the real-time clock says, okay, it's 12, it then stops forgetting and counting degrees and actually just basically moves until the micro switch. So it's reset, recalibrated every time. Minute hand, which is on another stepper motor, little one, that uses a reed switch and a magnet. So every time it needs to point at 60, it basically goes round until the reed switch moves, and then it can get, that means it can go round and round and round and round without being blocked by some great lump of a micro switch. To keep the climatic revelator in synchrony, there are a couple of reed switches again in the baseboard and a series of 5 magnets on the back of this carousel, so it can turn but know exactly where it is at all times. And then with the Gregorian scribulator, again, as you move this back, there's a little micro switch as this arm comes back to tell it where to start. And it does that every time it writes the day, date and month. It always goes back until the micro switch clicks. It knows whether the pen's lifted up or down, because just behind here there's another reed switch with a little magnet in this bit, so every time it rotates it knows where it is. And there's another one just back here with a magnet on the back of this disc and a reed switch underneath, so every time before it starts writing it goes around, finds where it is, and it can then start. So now let's talk about how to connect and control one of these wonderful little stepper motors from an Arduino. Now, because they've got 4 coils in the stepper motors, there's quite often, as they turn round, 2 are on at the same time to help it pull its way round. So they can draw about 330 milliamps if memory serves. So that's about 1/3 of an amp. Obviously that's way above the 20 milliamps the Arduino outputs can provide. So we need an interface. So here's what they always come with. Different companies make them, but they all look pretty much the same. They've got a ULN2003 chip on them, which has 7 electronic switches in. We only need 4. Come on to that later. That takes care of all the switching, lovely little sockets to connect the motor to, and even better, 4 small red LEDs. And they are very useful for 2 reasons. One is that when you've got all this installed and wired up and you're testing it and trying to work out where all the problems lie, it's very handy to check that you have got power, switching the right circuits on, and you are receiving proper signals from your Arduino. That's handy. They're also handy because if they go slowly you can get a sort of ripple effect, and you can build a window into things so you can see them from the front. Why waste such a brilliant resource? So to connect them up, you have 4 inputs connected to 4 of the digital outputs on the Arduino. They're only going to be on or off, and you have some power connections here. There's a minus and a plus, and it says underneath 5 to 12 volts. That means you connect the minus to 0 volts or ground, and you connect the plus to your 5 volts. There's a little link here that means if you unplug it, you can actually run a motor that could run off 12 volts. You can have a separate 12 volt supply to there, and you still need the 5 volts for the logic. But we won't worry about that, we'll leave that plugged in. It just connects the power supply to the motor to the 5 volts that we're supplying, so that's fine. I like pictures, they make things clear. So we have our Arduino powered by the USB plus 5 volts and 0 volt supplies. We have our 4 outputs and the 4 inputs to the ULN2003. Inside this board, basically, there's the ground connection to the power supply, like we said before, joined together. Inside this, the plus 5 volt supply from the power supply is constantly connected to the common connection to the motor, and it's the negative or 0 volts ground side of the coils that are switched. So just bear in mind, if you intend to use one of the other spare 3 electronic switches in one of these, remember it's switching ground. There's another little top tip to stop you getting caught out like I have. This is what one of these chips looks like inside. There are the 7 electronic switches, and they're little anti-flyback diodes that we talked about in the previous chapter, eons ago. And then there's the outputs. It always looks so much more complicated when you've got it all wired up, but it isn't. There's the motor, there's the interface board connected to the 4 Arduino outputs. I must have been feeling particularly uncreative this day, using green and yellow. I'd suggest use a different colour for each 4. And then the 2 grounds, 0 volts connected up, and the plus 5 to the thing, the interface. So to get this working, you don't need to use a library at all if you don't want to. You can write a sketch that will just switch on and off these 4 outputs in the right sequence, and that's absolutely fine. As I mentioned before, they can go as slowly as you want. They just can't go much faster than 12 RPM with these little motors. As always, there's a library available. Go to examples, and it's called Stepper. This is the one that comes with the Arduino. Stepper 1 Revolution, just do that. And what you find is it doesn't work, not with these small stepper motors. The lights flash, but the motor doesn't rotate, and that's a really important lesson. These motors are slightly different from other ones, primarily because they've got all the gears, but also the coils have to be run in the right order. And if you don't run them in the right order, you can hear it making a noise, but it's not actually going to rotate. I'll put the links to the 2 libraries in the description. I'll show you now what you can do with them. Here's the example that I've slightly changed from the CustomStepper library. At the top you've got the include library, then you've got defining or creating an object, or I've called it my stepper. You tell it which pins you want to the outputs. You then tell it, and this is very handy, how many steps or the configuration that you want each of the outputs to be for each step. So we've said we've got 8 steps. First one, these in binary, but you can see the first coil comes on, then the first and second coil comes on, then the second coil, then the second and third. You see the pattern, so it's drawing its way round. And then we've said there's 4,096 steps per revolution because of the gears. Just check that though. Because these little motors are produced by so many different companies, sometimes the gear ratios change, are different, and sometimes the coils are wired a different way around. So just be aware of that. Don't get caught out like I have on numerous occasions. And because I wanted to demonstrate and show what's actually happening with the coils switching on and off, I've made the revolutions per minute RPM 0.05 and set it to go clockwise. You can set that to CCW, which is counterclockwise. Then in setup, and you don't theoretically have to put this because I think the library takes care of it, but as I've said before, in setup I like to list all the pins that I'm using for inputs and outputs just as a reminder. So there we are, and then we come into the loop, which goes go round and round and round. My stepper, we set the direction, then we say rotate degrees 360, go right round. Then we're going to do that, and then after it's done that, my stepper set direction counterclockwise 360 degrees, go back again. In the examples for both of these libraries, it suggests that you put my stepper run in the loop, and then you can call all these other functions wherever you want. As long as my stepper run is in the loop, it will be called the right number of times and actually carry out the steps, the changes. Because my brain is a muscle, and because I just like to know where things are happening, I don't do it like that. I have a do while loop, always. So I tell it the direction and how many revolutions or how far to go. Do while not, which is the exclamation mark, my stepper is done. So keep doing whatever's in these brackets until my stepper has finished rotating. And then in there I put my stepper run. So it'll do that, then it'll change direction, then it'll go back. There's also another reason for having a do while loop like this, and I'll come on to that later. So let's upload this and see what it does. It's uploading. What a joy. That's lovely. So you can really see the sequence now as the 4 coils are pulling the centre round very, very slowly. You can't actually see it moving. So let's speed things up a bit just to prove that it is actually rotating. So I've changed the RPM to 5. Ooh, that's better. Now obviously when you have it going really fast, well, even relatively fast or even slow, you can't actually see the LEDs individually sort of sweeping along. But that's fine. Just seeing all 4 lit can be very helpful when it doesn't work, to narrow it down a bit. Isn't that lovely? Oh, the scope, the potential. It's mind-boggling what you can actually achieve with these things. Now, because I like to make all my machines look as though they're steam power and not just cheating with electricity, it's lovely if things speed up, accelerate, and then slow down in a sort of more mechanical way, more like a gauge does. And AccelStepper library does just that. Now this is a great library as well. So we're adding the library AccelStepper. It defaults to AccelStepper full 4 wire, 4 pins on 2, 3, 4, 5. That's the default value. This is a really powerful library that you can use to run all sorts of different types of stepper motor and stepper motors via much cleverer interfaces that just needs pulses and things. That's beyond the scope of this. We're going to say AccelStepper, my stepper, is going to have 8 steps and it's 2, 4, 3, 5. That's one thing to notice with this library. You mustn't have 2, 3, 4, 5. For some reason you swap the middle 2, then it works perfectly. As before, set the outputs. My stepper set maximum speed to 100. My stepper set acceleration to 20. This is the exciting bit because it can accelerate and decelerate. As before, I'm just going to go backwards and forwards. So this bottom bit in the loop, my stepper moved to, I'm going to tell it how many steps I want it to move. It works in a slightly different way, which is fine, rather than degrees or whatever. 4096, while, and again this is another one of these little loops that I use, while loops, while my stepper distance to go is not equal to 0, e.g. it hasn't reached 4096, keep revisiting it. Again, this library suggests you put my stepper run in the loop somewhere and then you can call all these other functions from elsewhere, but I do it like this. And then it's going to move to 0 to 0. So while my step hasn't reached 0, keep going. Let's give that a go then. Right, it's uploading. Oh look, isn't that lovely? That's the acceleration. And then once it's come to the end of a full revolution, revolution is it? It'll then slow back down again. Isn't that lovely? Let's have a look and see what that looks like. That's lovely. I'll try and get it going a bit faster and fiddle around with the numbers a bit. So I've changed the maximum speed to 300 and the acceleration to 50. Oh, and I've also got it to go less distance. So this is lovely because in addition to looking nice, it also reduces the wear and tear on the gears if they're sort of lifting or moving something fairly hefty. Rather than just going from stationary to full movement, it builds up acceleration. Isn't that nice? And the other lovely thing, as you might have noticed when I was showing you the chronological engine, because they slow down at each end, it looks lovely if you have a lens over the top with a little sort of cutout thing, because you then see it sort of moving, which looks interesting. As with all the libraries that I've talked about, do some research into them, because you'll find on GitHub lists of all the different functionality and functions that they offer. All the examples on the Arduino IDE cover a few, but by no means all of them. And I'm certainly not covering all of them here, just the salient few. Right, now, as I was whittering on about previously, we need a way of telling the Arduino where the motor is. It can be as accurate as anything, but if it doesn't know where it is, it's hopeless. So I've wired up a micro switch. Here's a micro switch with 2 blue wires on. So what we need to do is to sort out a way of getting this to tell the Arduino when the motor has reached a certain point. So the right way to go about this, you might think, would be to have a switch between the digital input on the Arduino and plus volts, but it isn't. You actually put a switch between the input and ground. There are several reasons for doing that. One is you've got grounds everywhere, and it means that even if you're sort of working from different voltages, you're still switching to ground. And to stop that floating, because one of the no-nos with digital electronics and microprocessors and things is you mustn't have any inputs floating. It doesn't like that because it doesn't know whether it's plus 5 volts or 0 volts or high or low in logic terms, so it can sort of oscillate and cause all sorts of strange problems. So what you could do is to wire a resistor, so a 10k resistor from there to plus volts. That means it's always going to be plus volts, it's always going to be high until you switch this switch, then it's going to pull it low, so it's never going to be floating. And it means sort of in effect connecting a 10k resistor across the power supply, but that's fine. If you use Ohm's law, V over IR, that is 5 volts over 10,000. And if you work that out, oh, the wonders of calculators, that equals 0.0005 amps. Ohm's law is always in ohms, volts and amps, which equals half a milliamp, so that's nothing. But because the Arduino is so wonderful, it even comes with built-in pull-up resistors inside that you can switch on or connect or disconnect from within your sketch. That's just amazing. So I've plugged in the micro switch to the Arduino ground and pin number 6. Everything else in this sketch is still the same, it's the previous one. This time I'm starting the serial link because I want to see what the switch is doing. Then I've set pin mode number 6, that's general purpose in-out connection, to input pull-up. And by doing that, if you have just input, you could let it float. But if you put input pull-up, it connects an internal resistor to pull it up to plus 5 volts when it's not being pulled down to ground. Then we go to loop and it's going to print whatever digital read number 6 is doing and delay 100. I've just commented out these two while we do that. So open the serial monitor window and you can see all the ones going down the screen. If I press the button, the micro switch, it goes to 0. So when the motor touches this switch and it goes to 0, to low, we need the motor to stop. So I've got rid of the serial bits and pieces. There's the input pull-up input number 6, setting the motor to 300, go nice and fast and all that. But in the loop at the bottom, I'm going to change this. I've said move to 5,000 because I know that's more than a whole revolution. So if I want to find out where the motor is, I need it to be able to move much further than I want to ensure that it is going to hit the switch at some point during its movement. Then I'm going to get rid of the distance to go because I don't care about that. I'm going to replace that with the switch. So now we've got while digital read 6 is high, that's the same as a 1, keep going. But once that's low, it's gone to 0, then stop and set my current position to 0. So all the other movements from then on will be relative to that point where the micro switch has been hit. I hope that sort of makes sense. I'll cover that in much more detail in the next video. Right, so it starts rotating until I click the micro switch, then it stops. The thing is, because it's in the loop, if I let go it's going to start again, and it's keep going to do that until it's done all 5,000 steps. What I'll do is I'll move that part of the code, this bit, into setup so it just runs once. So the loop is now empty and I've moved that into setup. Let's give that a go. So the sketch starts running. There you go. And that's fantastic because it's remembered now that that position is set to 0 from now on. I just keep thinking, just one more thing to point out. Now, the eagle-eyed amongst you will have noticed that some of the coils are left on once the motor's stopped. That's not a good idea because it's just going to use electricity and the motor will warm up. So, what can we do about that? So another handy feature of this library and the other library that I showed you is you can enable and disable outputs, and I always do that before I actually want to move a hand on a clock or something else, and after it's been moved. My stepper enable outputs, then it's going to start moving it all. Once it's set position to 0, my stepper disable outputs. Let's give that a go. So it's going to start moving and it stops and all the LEDs are off. That's definitely time to stop this video. Thanks very much for watching. I hope you found it informative and useful. I'm really looking forward to getting on with the next part where I'm going to fix the stepper motors down with the sensors and clock arms. We'll actually look at how to read the time from the real-time clock and get it to move the arms in hopefully some sort of sensible way. Hope to see you next time. Thanks again.